Good morning. On behalf of the RESILEX consortium, it is my great pleasure to welcome you to today's webinar on new PV solutions, battery components, and raw materials, the concrete results of the RESILEX project. This webinar focuses on critical raw material recovery, advanced photovoltaic recycling, and next generation of circular application for silicon. That it comes a particularly important moment for Europe. So recently, the European Commission is preparing the Circular Economy Act due for adoption in 2026, with the objective of creating a stronger single market for secondary raw materials, increase the supply of high-quality recycled materials, and stimulating also the demand from them across the European Union. And also the recent discussions from the European Commission also emphasized the recovery of critical raw materials from waste as an essential component of Europe's economic security and also industrial resilience. And at the same time, the implementation of the Critical Raw Materials Act is accelerating, reflecting growing interest in European projects for the extraction, processing, and recycling of strategic materials. And together, all of these measures send a clear signal that the future competitiveness of solar technologies will depend not only on performance and price, but also on carbon footprint, durability, recyclability, and responsible sourcing and European supply chain resilience. So this is specifically what is the context of RESILEX project, resilient enhancement for the silicon industry, leveraging the European matrix as entitled. And we address the silicon value chain as an interconnected system, from the recovery of value metals, from mining residues and waste waters, and going through the eco-design, and also to the recycling of end-of-life modules and the reuse of recovered silicon in advanced batteries. So today, I have the pleasure to give the floor to Mr. Giulio Pogliaroni, EU Project Manager from ETA, Florence Renewable Energies, who will moderate and guide us through today's program. So please, Giulio, the floor is yours. Thank you.
Thank you very much, Laura. So good morning. I'm Giulio Pogliaroni. I was in charge of the communication and dissemination activities of the RESILEX project. And today we want to bring you spot on the results and the next steps of the RESILEX project with some key figures in the project. Before starting, I would like to remind you that on our project website, you can find already a lot of materials and a lot of fact sheets and documents focusing on the results and the work done in the RESILEX, from fact sheets to public deliverables, and also videos, as well as the recording of our previous webinars. This is the 6th webinar in our series, so you have the previous 5 that focus on specific activities carried out in RESILEX. And this final one wants to be the wrap-up, where we take a look at each of the major components of the RESILEX project. So enough from my side. I would like to invite now the first speaker, which is Lidia Fernandez Rojo from Setaqua. She was responsible for the activities related to the recovery of critical raw materials from mining waste, and specifically in her role, they covered the recovery from wastewater from mining activities. So Lidia, the floor is yours. You can share your slide.
Thank you, Giulio, for the introduction. Today, I will speak about the critical raw materials recovery from mining waste. And first of all, I would like to introduce Setaqua. We are a research, development, and innovation network, based in 4 different places with the headquarters in Barcelona. And we have the objective of improve the water cycle in all the different stages. And in each one of the centers, we have the water utility involved in the governing board, as well as the local university and the Spanish Research Council. In in all of the places where we are located. There's also Veolia, which is a big engineering company, and it's because it is the parent company of the TACO. Now, going through the RESILEX results. First of all, I would like to remind the context and objective of the RESILEX project. This project was devoted to improve the resilience and sustainability of the value chain of silicon and other critical raw materials in Europe. So in this webinar, you will see, first of all, presentations devoted to the silicon. So there will be ones which will be dedicated to the solar panels, and especially to the silicon production, the photovoltaic waste recycling, and the eco-design of these solar panels. Then others that will be dedicated to the silicon composite for lithium-ion batteries. And then there's this short presentation that will be about the critical raw materials recovery from mining activities. And in this block, we have two different objectives. We have, and the first objective was to demonstrate the sustainable circular process to recover waste critical raw materials in the mining industry. And the second one was to assess the recovered secondary critical raw materials and develop a replication plan in other mining operations. This work was developed jointly by FETACWA, Tarsus Mining, and Imperial College London. Concerning the first objective, we developed a treatment train, which consisted of 8 different units, 6 of each within the wastewater valorization route operated by FETACWA, and 2 of them within the solid valorization route operated by Tarsus Mining. Here in the wastewater valorization route, we treated the water from Tarsus Mining, and in the solid valorization route, Tarsus Mining treated their mining waste. You can have a look at the YouTube video to see the successful development and operation of the resource recovery treatment train. The main outcomes of this treatment train was that we were able to remove up to 95% of the sulfate present in water and produce biogenic sulfite up to 300 milligrams per liter, which was used afterwards to precipitate in copper and zinc and recover them for further processing. Also, we were able to produce a stream that was no longer acidic compared with the original acidic wastewater. And if this treatment train was implemented on site, there will be a 90% reduction in acidic discharge compared with the untreated mining wastewater that is there today. However, there still will need some other refining or polishing step before this water can be reused. Then, as I said, with the biogenic sulfide produced, we were able to recover zinc and copper as a metal sulfide concentrate with 20% zinc and 6% copper. And these were suitable as an intermediate feedstock for the metallurgical industry. And then in the last step of the treatment train, we were also able to recover cobalt and nickel as hydrated sulfate salts with 80% cobalt and 6% nickel. And with this quality, these were able to be used as pigments in the case of cobalt or micronutrients in the case of nickel, as well as feedstock concentrates also for the metallurgical industry. However, battery-grade applications will require further processing. And for a solid valorization route, we were able to produce sulfuric acid from mining waste with a concentration about 30%. And this acid was able for internal reuse within the treatment train or the mining industry. And concerning the second objective, which was to assess the recovered metals and develop a replication plan, we developed a multi-criticalization analysis to assess the replicability of this technology across other companies, considering technical and sustainability criteria. And we assessed 4 different places where this train could be upscale, and 3 of them were identified as suitable. So the next step of this work package would be to reduce in general the operational cost of some steps, to facilitate its industrial implementation, also add further stages to produce the reusable water. As I said, we decrease the discharge into the acidic discharge into the environment, but there still will need the treatment tank still will need some polishing steps afterwards. Also, there we will need to improve the recovery stages to increase the purity of the recovered metals and the concentration of the sulfuric acid. And finally, the next step is to scale up the treatment train, fully or partially, towards a demonstration operational unit at the identified mining sites. So thank you very much for your attention.
Thank you very much, Lydia, for your presentation, very spot on. So I would like to remind you that we previously held a webinar together with Lydia and also the representative from Tarsis Mining. So if you want to dig deeper in these topics, we recommend you to catch up with that webinar and also the related fact sheets and public deliverables. Thank you, Lydia. Now we move to the next speaker, which will be Marie-Nicole from Group Comet. So here we are talking about another pillar of the RESILEX project, which is the recycling of end-of-life PV panels and the valorization of the materials in these panels. So Marie, please, the floor is yours. You can share the presentation.
Thank you, Julio, for the introduction. So as Julio said, Marie-Nicole from Comet Traitement. We're a recycling company in Belgium and involved for us in work package 5 about the recycling of the silicon from PV modules. And we were 4 partners in the work package. So Comet Traitement, the GM laboratory at the University of Liège, RECMA, and we're all 3 Belgians, and Envie2, who's a French company. So the collecting and recycling of end-of-life PV panels happen in 2 stages. The first stages is the dismantling process through automized and semi-automized dismantling benches done by Envie2 and RECMA to take the aluminum frames, the junction boxes, and the cables off. And then the laminates are sent to Comet for the recycling and the purification of materials, especially the silicone from the RESILEX project with the University of Liège. So we recover the components individually, metals, silicone, glass, and the plastics. I will talk about plastics, and I mean EVA and backsheet together. So the first part of the work package was desk research on the state, the actual state and the predicted state of the PV panel, end-of-life PV panel market in Europe. And as you can see on the graphic, like this is going to the estimated cumulative waste by country is going to increase exponentially in the next 20 years. We already see it happening, and it's going to accumulate at more than 1 million tons in Germany. Germany would be actually, if I can say, the champion in that, but other countries are installing more and more panels, and from all over Europe, not just Western Europe. As for us, here I'm showing you something so you can have in mind what we actually receive. So I have to precise that we actually receive a third, Comet and Envie actually receive roughly a third of the French end-of-life PV panels. And Comet and RECMA recover the Walloon market for end-of-life PV panels. So as you can see, the first few years up until 2025 were not that much, but we've seen an explosion, if I can say, in the amount recovered, and we are most likely going to be over 6,000 tons this year. So after that, the operating process itself. So we had two focus. We were focused on two things. So first, for RECMA, it was to improve their actual bench and also commission a fully automatized dismantling bench. As I said, to recover the frames and the cables and the junction boxes, to have a better ergonomics and better productivity. The second part, which is the recycling itself, is, if I can say so, actually at Comet we do fully mechanical, so there's no chemical recycling. So we are going to shred the laminates, and through separation we are going to recover glass, metal, and plastics. And thanks to the RESILEX project, we are adding the silicone, the recovery of silicone, and the test for the purification of that silicone were done with the GEM laboratory at the University of Liège, and we can recover silicone up to metallurgical grade, as it's said. So for visual sakes, the silicone actually showed is not exactly the state we are going to we are recovering it. So it's smaller, but then you couldn't see anything there. So now that we have all of that recovered, we have obviously projects in mind, and we have two focuses. The first is with the R&D. So RECMA is focused on two subjects, which is obviously the improvement of their actual benches for better automation and ergonomics, and then the reuse through R&D projects. And the reuse part is quite important because we see that many panels are still operational after collection when they are collected well from the field. And actually, one of the keys for better resilience and sustainability of the silicone, and by extension CRMs, value chains, is to reuse still functioning panels to lower the demand in new CRMs, because if we reuse more, we will produce less brand new panels. As for Comet, we are involved in European projects, especially the WISER project with RECMA and NTNU, which is also a partner in RESILEX. We are going to focus on specifically recovering silver from the silicone and use that silicone to produce new silicone crystals again, and then recover the antimony from the glass. One, to help close the loop to glass manufacturers, and on the second hand, to also use the glass to produce new silicon crystals. And then the bigger part concerning Comet and Envidoso will be industrial, because we are teaming up to start a new mechanical treatment plant in the south of France. The startup is scheduled for 2028 with future treatment throughput of 16,000 tons a year. We will obviously recover individually aluminum frames, cables, junction boxes, metals, ribbons and welds, of course, the silicone and the glass. And we will use several technologies that we are already using, and obviously the silicon purification technology that we developed during RESILEX. And that's all for us.
Thank you very much, Marie. Again, there are some materials already published on the RESILEX website that delve deeper into the work done by Marie and the Comet group, so I encourage you to have a look. Now we move to the third speaker, which is Adeline Lanterne from CEA Ines Solar. They have worked on the eco-design of PV panels and on the reduction of the critical raw materials used in the PV panels. So, Adeline, the floor is yours. You're still muted, Madeline.
Thanks, sorry. Thank you, Giulio, for the introduction. And now I will discuss about how we reduce critical raw materials for the next generation of eco-design PV in the project. This was done inside Work Package 4, where we have to demonstrate sustainable and eco-design PV solar cells and modules with 3 main objectives. The first objective was concerning one critical material, which is silicon. And there we had to assess in the project new wafers fabricated from revalorized silicon waste in the project to process high-efficiency solar cells. Our second objective was to develop more sustainable silicon solar cells by reducing the silver and indium content, which are 2 other critical materials for this application. And we did this in a heterojunction solar cell. And finally, our third objective was to investigate biosourced materials for low environmental footprints photovoltaics module. I will present a few results we had yes. And for this, we were 3 partners in the project, CSCM in Switzerland and LMGP laboratory in Grenoble in France and CEA in France. So first, a few results we had at CEA on the recycled silicon part. Here we have the picture of an ingot that was grown at CEA in the project. So it's a 30 kilogram Chokalski ingot, where we incorporated 12% of recycled silicon produced at NTNU University in Norway in the project. So it's a silicon which is very particular because it was processed with a low CO2 emission process and using revalorized silicon waste. And this recycled silicon, they managed to reach a purity of 5N in the project, and so we could use it to grow this ingot with properties suitable for solar cell application. And so that was our first success. And then we sliced the whole ingot into wafer. And in the end, we process heterojunction solar cells on this wafer. The fact that it's a purity which is lower than what we are used to work with. We have many new impurities in this silicon, and so we had to add pre-treatment on the wafer to improve the performances of the wafer. And in the end, we managed to reach the same performance than industrial standard Chokalski N-type wafer by And thanks to this, we reach a 23.3% efficiency on this cell. So this was the first important proof of concept using this recycled silicon, and also a first step towards a new circular models for silicon in Europe here. If now I will present few results about how we reduce indium content in the project. For that, we worked on several aspects, but here I present only an approach where we reach very high TRL in a project. It's an approach where we reduce the indium containing layer, which are the ITO layer in blue in the cell, and here, and we reduce its thickness from 100 nanometers to 15 on the front, and we combine this with a silicon nitride layer to keep very good anti-reflection properties. And thanks to this, we optimize this, in the project, and we reach a point where we have near no efficiency losses with a 77.2% indium reduction in content. We have only 0.08% absolute of efficiency losses, and we could validate this in the project on large batches on CA pilot line, and the process was also optimized for having good stability under humidity, and also optimized in order that we could pass a standard aging test in module configuration. So that was one important result here. And if I now continue on silver reduction for solar cells. In the project, we also work on several approaches. The one I'm presenting here is also the one where we reach high TRL, like TRL 7, I think. And here, the approach is to incorporate silver-coated copper core particles into the electrode. Usually the electrode is made only of silver, and here we have silver and copper inside it. So we apply this either on the rear side of the cells or on both sides. And on the graph here, you can see the silver content per watt, how we could reduce it, and the impact on the cell efficiency. In the end, we could demonstrate solar cells with 72% silver reduction, so we reach 7 milligrams of silver per watt. And we could validate the approach for reduction of 55% of silver approximately, where here we have no efficiency loss, and we also could confirm for this particular configuration that we have stable performance through standard aging test. Finally, in the project, we had another important results where we implemented this innovation in a 60 solar cells module demonstrator. For that, we implemented the results where we reduce indium of 72%, the approach where we reduce silver by 50%, and we combine this with a European silicon wafer, all processed on CA pilot line, and this was then interconnected with lead-free approach, which is ECA with copper ribbons, and we combine that with bio-based materials that have been identified and validated in the project. For instance, we used a timber frame instead of aluminum frame. We replaced the encapsulant standard POE by TPO, which is a thermoplastic olefin film, which was partly biosourced, and also we use a European fluor-free backsheet. And with all this, we have here our results of the demonstrator, which is we had a successful lamination of all the materials, and we end up with EcoDesign's 325 watts module. With this module, the most important thing here is that all the innovation implemented have been checked that we could pass a standard aging test. And so here for this optimized bill of material, we also passed a standard aging test according to the ESC standards. So that was one important result. If now I say a few words about our next steps concerning the silicon impact reduction, due to the fact that we have more impurities, as I said before, in these materials, we have a specific issue with the boron content, which is very high in this recycled silicon. And so next step could be to further reduce this boron content or in the recycled silicon, or to improve the pre-treatment that we have developed in the project to reduce even more the impact of this boron on the solar cell performance and especially the solar cells stability under light. So this is one point. Also now one of the next steps is to investigate the stability of the solar cells fabricated from this recycled silicon wafer in module configuration. Concerning now the production of more sustainable solar cells with silver and indium reduction. So I presented you results of high TRL where we could have low indium and low silver processes, and now the next step is to support and promote the industrial transfer of these two processes. Another next step is to further develop promising approach that have been also developed in the project and not presented here, where we could reach indium-free solar cells or silver-free solar cells. And for some of them, we have very promising results. For instance, at LMGP, they develop indium-free indium-free layers, TCO layers, with new techniques for the deposition, which is AP-SALD. And so we had promising results with these layers. Also at CSEM, they had very nice results and high efficiency IBC heterojunction solar cells without indium, so indium-free heterojunction IBC. And now their next step is to further reduce the silver content in these cells. And also concerning the next step is to further reduce the silver content. One objective we know in order to have very sustainable production of photovoltaics in large quantity is to reduce the silver content down to 1 milligram of silver per watt. And for that, one promising approach that should be further developed is the use of pure copper paste. Finally, a few words about next steps concerning the investigated biosource materials. For that, there is still many tests ongoing, and that should be further continue to validate these new materials, especially for the front sheet, the encapsulant, or the back sheet. There was materials developed at CSEM in the project that are still under test and that have been show very promising results, and also some of the layers selected by CA in the project. And finally, there was no outdoor testing of the eco-design module in the project, so one of the next steps is to perform this outdoor testing with the selected bio-based materials. And thanks for your attention.
Thank you very much, Adeline. I would like to remind that there is a webinar where Adeline focused on these topics in detail together with the colleagues from CSEM. Now we can move to the next speaker. In the meantime, I would like to remind you, if you have some quick short questions, you can address this in the Q&A tab. And now we move on to the last speaker, which is Hamid Ubaha from University of Liège. Welcome, Hamid. So the floor is yours.
Can you hear me?
Yeah. Okay.
Thank you, Julio, for the presentation and for organizing this final webinar for RESILEX. So here in this presentation, I will share with you another way to valorize the silicon recovered from end-of-life PV panels, and by exploiting the chemical reaction between silicon and lithium, and show you how to integrate the silicon as lithium storage material for lithium-ion batteries. So why we are interested in silicon for lithium-ion batteries? Actually, the reaction between lithium and silicon is known since 70s, and one atom silicon can actually react with 4 lithium of lithium, and this leads to high capacity, more or less 10 times than the commercial available and used graphite, where one lithium needs 6 atoms of carbon to be stored. Another property of silicon is that the silicon alloy, when it reacts with lithium, has a relatively low potential, which leads to high energy density. However, the silicon has some drawbacks. Actually, silicon is so good in storing lithium that its volume, the volume of the particles can expand to up to 300% during the lithiation, and this shrinking and expansion of the particles can lead to the pulverization and failure of the electrodes. So the key is to find a way to stabilize these silicon particles when it's used for the lithium storage. There is many the different strategies that are reported in the literature. Some are already in pilot scale production, including innovative electrolyte production, or working in the specific polymers as novel binders. We have people that were also working in surface engineering of the particles, or also the structure of the silicon itself. In the RESILEX project, we opted to synergy of 2 technologies that we call it particle engineering strategy, where nanostructuring is combined to the silicon carbon composite formation, and we developed and optimized a scalable process to transform and to convert the recovered silicon, which that Marie speaks about, from end-of-life PV panels and to an industrially relevant spray drying process. And the final composite was also demonstrated in pouch cell, practical pouch cells, with the collaboration with CA and CCM as our partners in the WP6. So with the RESILEX project funding and support, we are now at University of Liège. We are able to take a step further in the silicon composite production, reaching a TRL of 6 to 7 now, and we are now able to produce more than 1.5 kilogram per week with a good yield. So the proposed approach in RESILEX combines pilot scale mailing, an industrial spray drying process, and the controlled pyrolysis, and this allowed us to produce silicon carbon composite with tailored particle size and morphology. The electrochemical properties of our composite, as I said, were evaluated thanks to our collaboration with the CA, where they produced electrodes at industrially relevant conditions. You can see that they can produce double-sided coating using our silicon in their facilities with a length of up to 13 meters with a width of 12 centimeters. So it's like we are close to the industrial actually production. And there they assembled a multi-layer pouch cell of 5 to 5 format, and the electrochemical properties were evaluated in both CA and CCM to validate the composite. And also during this RESILEX project, we also used the silicon to produce some other electrodes, like the combining with silicon composite with the graphene oxide as a protective layer, and this was published in Journal of Power Source. Another way is to prepare hybrid anodes using this composite and tin disulfide. So another paper that is submitted is the scale up of production and the pouch cell evaluation results that now it's submitted to Advanced Science. I hope that it will pass. Finally, what we achieved is that now we have a pilot scale production of the silicon composite, and we can produce enough material for an industrial level. We're using the spread drying process. We have at CA the roll-to-roll electrode processing and the calendering that is also close to the industrial level. We have validation at multi-layer pouch cell of the composite. What is the next step to do is now for the silicon production itself at University Liège, we are a university laboratory, so we are not we don't have manpower or means to produce 100 kilograms, but we are at kilogram scale. But the next step to do is the continuous manufacturing qualification. Is when you pass from lab and pilot scale production to an industrial production, it's like a heavy lift. So you need a lot of qualifications and optimization. So we have also the reproducibility. We assess the reproducibility of our composite by producing different batches, but it's kilogram scale, different in different period of the year. Also, this was reproducible, but when you go to the big scale, you need also to secure this reproducibility of the production. And also for the electrochemical evaluation aspect, we need large format cell. We need to go farther than 2 ampere hours. So we have close to the practical cells. We need also to work with the high capacity cells. We need also to do safety tests and increase also the amount of silicon in the electrode. Thank you for your listening.
Thank you very much, Hamid. There is one question perhaps for Marie. They ask if you have data on PV waste in Portugal. So I guess if you have data or also a prospect on the current flows of PV waste now available in Europe.
So I went to check, and actually we do not have. Sorry, we have Spain. We have Spain and prospect in Spain, but not Portugal.
Mm-hmm. Thank you. And also, I would like to remind one thing that emerged in our recent activities, and it's outlined in some of the documents and policy summaries that we have issued, that the flow of waste, of PV waste across European countries is still a tricky thing. And we would need a Schengen of waste in order to scale up these value chains. So thank you very much. Now I will give the floor to Laura for her closing remarks, and then we will end this webinar.
Thank you all. Well, I think in today's session we can see how these demonstrations that it's not a simply an end-of-life activity. It begins with also material selection and product design, and continues through collection, separation, and purification procedures. And also, what we want is also it is being developed to create also for industrial applications and markets. And we really hope that today's presentation will encourage more discussions, not only about from the point of view of the technical achievements, but also about, as Julio mentioned, what is required to bring these solutions also to industrial scale, supportive regulation, investment, access to waste streams, and also other quality standards and market demand. Again, thank you for joining us, and I would like also to and to congratulate to the RESILEX consortia, and I would like to express my appreciation to CETACUA, COMET, CEA today, the University of Liège, and for sure Julio from ETA to make it possible. And also, most important, thank you to all who follow us during the duration of the project, and also to contribute with different perspectives, not only from the European Commission, but also in other forums. And for that, I would like to thank you all your collaboration and cooperative efforts. So thank you. And I consider the webinar is now officially closed.
Thank you, Laura. Thank you to our speakers. Thank you to the attendees, and see you next time.
Thank you.
Thank you all.
Thank you. Bye-bye.